All right, we're going to take a look at section 2.2, which deals with polynomial functions of higher degree. In the previous lesson, we looked at quadratic functions, which are polynomial functions of degree 2. Today, we're going to look at polynomial functions of degree 3 or higher. We're going to look at some terminology that we're going to use, as well as how we go about sketching the graphs of polynomial functions of this type. Okay, so first let's start with the definition of a polynomial function. So a polynomial function is a function of the form. The notation looks very confusing, but it's not. This is how math books define a polynomial function. So it's going to be a function of the form f of x equal to a sub n times x raised to the n power plus a sub n minus 1 times x raised to the n minus 1 power plus all the way out to a sub 1 times x plus a sub 0, where all of those a values, so a sub n minus 1, all the way out to a sub 1 and a sub 0, those are just real number coefficients. And your exponents n have to be non-negative integers. Okay, and as we've mentioned many times in the last two chapters, the domain of any polynomial function is the set of x, such that x is a real number. Okay, so the reason we can't have negative integers as our exponent is if we have x raised to the negative 1 power, that term is not going to be a polynomial. X to the negative 1 power, we can rewrite that as 1 over x, and that is going to be a rational function, not a polynomial function. And we also can't have fractions as exponents as well, because we can take like x to the 2/3 power, and if I rewrite that in the form of a radical, that's equivalent to the cube root of x squared. Again, we're not looking at a polynomial function there, we are looking at a radical function, namely a cube root function. Okay, so our integers have to be, our exponents have to be non-negative integers for polynomials. All right, the graph of every polynomial function is smooth and continuous. Okay, so the graph of every polynomial function is smooth and continuous. We're going to talk like in the next chapter, in chapter 3, when we get into calculus, what it means for a function to be continuous. Like there's a specific mathematical definition for that. But right now, we have to work with like a more simplified definition. So when we say the graph is smooth, the graph is smooth means that if your graph changes direction, okay, like we have here going from increasing to decreasing, it's going to do so in the shape of a curve, all right? And continuous means I should be able to draw this graph of a polynomial function without lifting my writing utensil. Okay, so I should be able to complete that entire graph without lifting my writing utensil. So that's going to be your working definition for the function being continuous for the time being. Okay, now there are 4 features that you're never going to see on the graph of a polynomial function. The first one being a corner. So you can think of a corner as a point where 2 segments meet. Okay, so your polynomial function will never have a corner. The second feature that you'll never see on the graph of a polynomial function is what we have here, and that's called a cusp. So if a corner is a point where 2 segments meet, a cusp is going to be a point where 2 curves meet. Okay, the third feature you'll never see on the graph of a polynomial function is what's called a gap. Okay, so that's going to be like a jump in between 2 y values on the graph. So you'll never see a gap on a polynomial function. And then the fourth feature you'll never see on a polynomial function is a hole. And you guys should have seen holes on graphs last year, namely whenever you were looking at the graphs of some types of rational functions. Okay. So next thing we're going to look at are what we call power functions. Okay, so power functions are defined as functions of the form f of x equal to a times x raised to the n power, where a is a real number a cannot be equal to 0, and n, which is greater than 0, is an integer. So you can think of a power function as being a polynomial function that only has one term. Okay, so again, a power function is a polynomial function that has only one term. All right, so what we're going to do is we're going to take a look at properties of power functions. And we're going to make like a table to look at these properties. So on the left-hand side, we have y is equal to x raised to the n power, where n is an even integer. And y is equal to, on the right-hand side, x to the n power, where n is an odd integer. Okay, so what we're going to do is we're going to take a look at a function of each of these types that we're familiar with. So x to the n power, where n is an even integer. I think the best function to look at for that is the function y is equal to x squared. So I'm going to draw that graph in red. And then for y is equal to x to the n power, where n is an odd integer, I'm going to look at the function y is equal to x cubed for that. Okay, so graphically, that function is going to look like so. Okay, so what we're going to do is we're going to take these two functions and we're going to generalize some properties that functions of each of these types possess. Okay, so we'll start on the left-hand side. Okay, so x to the n power, where n is an even integer. If we look at the function y is equal to x squared, we should see that that graph is symmetric with respect to the y-axis. And if our function has y-axis symmetry, that means that the function is an even function. Okay, so when we look at the domain of this function, when we look at the x values that get covered up by the graph, that's going to be the set of x such that x is a real number. If you want to write that in interval notation, that's fine as well. Set or interval notation is acceptable for me. When we write the range, so when we look at the y values that get covered up, the range is going to be the set of y such that y is greater than or equal to 0. Okay, when we look at the 3 points that lie on any graph of y is equal to x to the n power, where n is an even integer, when I input 1 into the function, when I input -1, -1 squared is going to give me an output of +1. When I input 0 into the function, 0 squared gives me an output of 0. And when I input 1 into the function, 1 squared gives me an output of 1. Okay, and then statement number 4 says as n increases. So as our exponent gets bigger, the graph becomes more vertical. When our x values are less than -1, or when the x values are bigger than 1, and lies closer to the x-axis near the origin. Okay, so what that means is if I were to compare the graph of y is equal to x squared to the graph of y is equal to x to the 4th power, I'm going to do the graph of x to the 4th power in green. Both of those graphs are going to contain the 3 points that we mentioned before. So -1, 1, 0, 0, and 1, 1. But the graph of x to the 4th power in between the x values of -1 and +1, that graph is going to lie closer to the x-axis. So that graph kind of gets compressed against the x-axis. And when the x values are smaller than -1 or bigger than 1, that graph is more vertical. Okay, so graphically, the function x to the 4th is going to look like that relative to the graph of y is equal to x squared. Okay, So we're going to do the same properties for x to the n power, where n is an odd integer. Okay, so we're going to look at the graph of x cubed, and then we're going to state some general properties based on our observation of that graph. So number one, the graph is symmetric with respect to, when we look, we see that that graph has origin symmetry. So with respect to the origin, and if the graph has origin symmetry, that means that the function is an odd function. Okay, so when we look at the domain of that function, the x values that get covered up by that graph are the set of x such that x is a real number. The range values are the y values that get covered up by that graph. So the range of that function is going to be the set of y such that y is a real number. So that graph is going to hit all x values and all y values. Okay, if we want the 3 points on the graph of that function, when I input -1 in the place of x, -1 cubed gives me an output of -1. When I input 0, 0 cubed gives me an output of 0. And then when I input 1, 1 cubed gives me an output of 1. So those are the 3 points on the graph of that function. And then property 4, I didn't feel like writing all of that out again, but it's going to be exactly the same for x to the n power, where n is an odd integer. So if I were to compare the function of y is equal to x cubed, which is in red, to y is equal to x to the 5th, which I'm going to graph in green, the graph of x to the 5th is going to contain the same 3 points. So -1, -1, 0, 0, and 1, 1. In between the x values of -1 and 1, that graph is going to lie closer to the x-axis. Okay, so that part of the graph like gets compressed against the x-axis. And then when the x values are smaller than -1, or when the x values are bigger than 1, that graph is going to be more vertical. So that graph is going to grow faster, like so. Okay, so that's how the graph of x to the 5th power would compare to the graph of x cubed. Okay, so next we're going to let f be a polynomial function and r be a real number. So again, if we let f be a polynomial function and r be a real number, if f of r is equal to 0, okay, so if we input r into our function and it gives us an output of 0, then we can say that r is a 0 of the function f. R is also a root of the function f, and r is an x-intercept of the function f. So when you see 0 or root or x-intercept, those are all synonyms. They mean the same thing. Okay, so those are values that make your function 0. And if r is an x-intercept of f, then x minus r is a factor of the function f. All right, so again, if r is an x-intercept of the function f, then x minus that number, x minus r, is going to be a factor of f. Now, when it comes to graphing polynomial functions, if your function has an x-intercept, the graph of your polynomial function can do one of two things at an x-intercept. Okay, it's possible. Let's say our graph has x-intercepts where I've marked in green at those points. So the two things that can happen to the graph of a polynomial function at an x-intercept is the graph can cross the x-axis. Okay, so here our graph crosses the x-axis. Or the second possibility is that the graph can touch the x-axis at an x-intercept. Okay, and here's an example of where the graph touches the x-axis. And if you guys remember from last year, like what helps us determine whether a graph touches or crosses the x-axis at an x-intercept, that is the multiplicity of your zero. Okay, so let's take a look at multiplicity. So if x minus r raised to the m power is a factor of the polynomial f, then we can say r is a zero of multiplicity m of the function f. Okay, so like we said before, if x minus r is a factor, then r has to be a zero or a root or an x-intercept. The exponent of that factor tells us the multiplicity of that zero. Okay, so if r is a zero of even multiplicity, so if the exponent for your factor is an even number, that tells you that the graph touches the x-axis at x is equal to r. And if r is a zero of odd multiplicity, so if x minus r has an exponent that is an odd number, that tells us that the graph crosses the x-axis at x is equal to r. All right, so we're going to take a look at a couple of examples involving this in the next video.